For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@solidworksassignmenthelp.com or reach us at https://www.solidworksassignmenthelp.com. Problem 1. A fatigue crack growth test was done on a compact tension specimen of a hard HRC equals 60 tool steel. A table of respective values of stress intensity factor range, delta Ki, and corresponding fatigue crack growth rates, d/dn, are given in the table. Plot these points on log-log coordinates over a suitable range and graphically estimate values of the Paris law fitting constants A and M that decrib E. Problem. Estimate values of the Paris law fitting constants A and M that decrib E fatigue crack growth in this material according to. Be sure to give appropriate units. Use a least squares fit to the dataset to obtain refined values for A and M. For the least squares best fit to the Paris law constants, decrib E how you would obtain an alternative set of parameters delta 0, delta Ki 0, and M that equivalently describe fatigue crack growth according to. And give numerical values for all parameters. Based on Dowling text, Problem 11.3. SolidWorksAssignmentHelp.com. Problem 2. An edge crack of initial length AI equals 3 mm exists in a large plate that is to be subjected to a remote cyclic stress, sigma infinity, ranging from min equals 0 to some Tobe-determined maximum value of max, R equals 0. You may assume that the plate is sufficiently large that the configuration correction factor Q equals 1.12 in the expression for Ki for all crack length values, A, to be considered. The fracture toughness of the material is KIC equals 115 MPa square root m and its yield tensile strength is sigma y equals 1045 MPa. Fatigue crack growth is decrib ed by a Paris law form. It is desired to be able to apply n equals 50, 000 load cycles to the pre-cracked structure while still retaining a factor of safety of at least second on the actual fatigue crack propagation life until fracture. That is, it is desired that the predicted fatigue crack propagation life for the chosen value of max be at least greater than or equal to 100,000 cycles. What is the largest value of max that meets this constraint? Note, this problem is a bit non-standard in that the upper limit of the fatigue crack length AF depends explicitly on the unknown value of max. Why is this so? But so does the number of cycles, NI-AF, required to propagate the crack. You may find it desirable to manipulate the relevant equations in a form suitable for numerical iteration or graphical solution. For your chosen value of max, make a graph of the crack length A(n) for 0 less than or equal to n less than or equal to 100,000 cycles. What is the predicted value of crack length at n equals 50,000 cycles, A(n) equals 50,000, and what is the corresponding value of Ki? Based on this Ki value. SolidWorksAssignmentHelp.com. What is the predicted factor of safety with respect to fracture at this point, i.e., what is the ratio of KIC/Ki max A(n) equals 50,000? What conclusions do you draw about the distinction between factors of safety on fatigue crack propagation life and on fracture itself? Discuss. SolidWorksAssignmentHelp.com. Problem 1 Part A. Results are shown in Figure 1. MATLAB scripts for Part A and B are attached. Graphically square root estimated fitting constants are A equals 9.5737 times 10⁻12 m/cycle, MPa m equals 3.17144. Part B. square root least squares fitted constants are A equals 8.8497 times 10 minus 12, m/cycle, MPAM, m equals 3.21473 part C. With the data for part B, the Paris law is given as following. 1. Solutions. Paris law can be rewritten as 2. Where increment A0 is identical to dn0 is the corresponding reference crack growth rate, and increment Ki0 is a reference crack driving force. Increment Ki0 and increment A0 are the values of any point on the power law growth square root rate curve. If we choose increment Ki0 equals 6.0 MPAM, the corresponding increment A0 equals a times increment KIM0 equals 2.8085 times 10 minus 9 m/cycle, and m does not change. SolidWorks assignment help.com d/dn m/cycle. Figure 1 d/dn versus dki 10.7. 10.8 d/dn m/cycle. 109 101 dk MPA asterisk m 0.5 I. SolidWorks assignment help.com. Problem 1. d_dn equals 1e6 asterisk 4.26 9.12 17.5 35.1 % unit mm/cycle delta ki sad face 6.84 8.76 10.35 13.3 % unit MPAM 0.5 % part 1. Plot these points on log coordinates and graphically estimate % values of the Paris law fitting constants A and M. Log delta ki d_dn/1000 asterisk dash title figure 01 d/dn versus \delta k_i label \delta k_i MPA asterisk m 0.5 a label d/dn m/cycle grid on hold on. % estimate of A and M using first and last point. M equals log d_dn 4 / d_dn 1 / log delta ki 4 / delta ki 1 a sad face d_dn 1 / 1000 / delta ki 1 m dsp sprint estimate of A asterisk delta ki m A equals %g m/cycle / MPA asterisk m 0.5 m equals %g a m. % part 2. Use a least squares fit to the dataset to obtain refined values % for A and M. SolidWorks assignment help.com. P equals polyfit log 10 delta ki log 10 d_dn/1000 1. DASP sprint best fit of A asterisk delta ki m A equals %g m/cycle / MPA asterisk m 0.5 m equals %g comma 10 p 2 p 1. SolidWorks assignment help.com. Problem 2 part A integration of the crack growth equation we get. Since Q is a constant, the above equation is reduced to where AF is a function of the maximum stress, substitution of AF and increment sigma equals max into the expression of NIAF, and rearrange the equation, we get the following expression. In the above equation, AI equals 3 mm, increment AO equals 10 minus 5 mm/cycle, increment KIO equals 20 MPAM, and NIAF equals 100,000. Substitution of the above numbers, we get the equation to solve for max. N versus max is plotted in figure 2.